In this video, I'm going to be introducing some basic derivative rules. They're called the power rule, the constant rule, and the sum and difference rule. First, before we do that, let's make sure we understand some notation when we find derivatives, so we can understand the questions when they ask us to do that. We started with our slope formula, change in y over change of x, and we're going to find the limit as the change of x approaches 0. That's representing the slope of that tangent line. You could also represent it using the difference quotient, but really all of that could be simplified to this simple notation where we just put an apostrophe next to the function name, and that represents the derivative of f, or the derivative of the function f. When we want to take a derivative, we use this symbol or notation, and it just simply means that we're deriving something with respect to the input variable. So this, for example, would be deriving with respect to x. We could derive with different variables, so that letter may change, but it still means find the derivative or take the derivative. We could find derivatives of entire functions. So if I want to find the derivative of a function, I use this notation symbolizing that I'm taking the derivative of some function, and that answer is going to be represented using the notation of the derivative. We can find the derivative of functions using this notation of a function. If a function is written with a y, we could find the derivative of y with respect to x. We could use that notation, or we could just use the y apostrophe. They mean the same thing. We could use functions that look, or a notation that has f of x, or just simply f. It doesn't matter. And then this lesser used notation, it also means find the derivative of the function y with respect to x. We won't see this notation very much. We will much more see apostrophes used, or this quotient right here. The first rule, most important rule, is called the power rule. The power rule is used anytime you're finding the derivative of a function with an exponent, or raised to a power. What you're going to do when you find the derivative is you're going to move that exponent value to the front and multiply, and then you're going to subtract 1 from the exponent value. So let's do this example over here first. So we're going to find the function, the derivative of function f, which is x to the 5th. We're going to move that exponent 5 to the front, and we're going to subtract 1 from that exponent. So we end up with 5x to the 4th. So we write the derivative of function f is 5x to the 4th. This is representing the slope or instantaneous rate of change at any point on that function. All we got to do is plug in an x value, and we can find a specific slope at that point. If we look at the most basic linear function, it's just x. It has a slope of 1. Starts at the origin, goes up 1 over 1. If I want to find the derivative or the rate of change of that function, we're going to take that invisible 1, move it to the front. I'm going to subtract 1 from that exponent, and we end up with 1 times x to the 0 power. And anything to the 0 power is just going to be 1, so we end up with just the coefficient, which is just 1. And that represents the slope of a linear function, the coefficient of that variable x. The derivative of a linear function is a constant, and when we graph derivatives, we'll emphasize that a lot more. Functions with radicals present a unique challenge in that we have to rewrite the radical as an exponent instead, and then we can use the power rule. So the square root of x is just x to the 1/2. If I apply the power rule, I move that exponent down to the front and subtract 1 from the exponent. Just be careful when you're subtracting fractions, you get that common denominator. So 1/2 minus 1 is the same as 1/2 minus 2/2, and then we end up with 1/2 x to the negative 1/2. So we could leave our derivative in that form, or we could convert it back to radical form, depending on how we want to work with it. Remember that a negative exponent just drops something down to the bottom, of a fraction, or if it's on the bottom as a negative, we would move it to the top. So we're going to drop this x to the 1/2 down, right down there with that 2 that was already there, and then we can just rewrite it as a radical, so we end up with 1 over 2 times the square root of x. Either form is okay, just depends on how you want to work with it. A constant rule is a unique rule, and it's a pretty easy rule. It's saying that if you try and find the derivative of some constant number, like an integer or a fraction, what you're really doing when you find the derivative is finding the slope of something. And the slope of a constant function is 0, because a constant function is just a horizontal line. If I was to say y equals 3, that would be a horizontal line running through the y-axis at 3. And the slope of a horizontal line is always 0. So the derivative of a constant or horizontal line is going to be 0. So anytime you take the derivative of a constant number, just replace it with 0. If we have a coefficient in front of our function, there's a long way to think about it, and then there's a short way. So I'll try and do them both. If we want to find the derivative of a function that has a coefficient, we ignore that coefficient and we just find the derivative of the variable function, that input function. So shift that 4 off to the side, ignore it for a second. Just find the derivative of the variable x squared. The derivative of x squared is 2x, and then multiply that 4 back in, and we get 8x. So that's kind of the long way of thinking about it, but really, if you just drop that exponent down and multiply it by your coefficients, it's just a much easier way of thinking about it. If your variable is in the denominator position, we're going to rewrite functions using negative exponents so that we can apply the power rule. So 2 over x could be rewritten as 2x to the negative 1. If I use my power rule now, find the derivative. I'm going to drop that exponent down, multiply it by the coefficient, I get negative 2. And then subtract 1 from my exponent, and I end up with negative 2x to the negative 2, which we could leave in that form, or we could rewrite it as a fraction again and say negative 2 over x squared. Again, either way you want to work with it is fine. Constants in front can get a little tricky when they're fractions. It's always best to just move that fraction constant out to the front, rewrite it, and again, just apply the power rule. So I'm dropping that 2 down in front and multiplying it by 4/5. The derivative of t squared is 2t, and then 2 times 4/5 gives us 8/5 t. Sum and difference rule is the last rule we're going to talk about in this video. It simply says that if you have an equation or a function or an expression that has multiple terms in it, as long as they are being added or subtracted, you can find the derivative of each individual term separately and put it all back together. So for example, I got this long polynomial function called y. I'm going to find the derivative of y with respect to t, because t is the input variable. If it was x, it would be find the derivative of y with respect to x. So that bottom is just talking about what our input variable is. So I could just find the derivative of each individual term because they're being added or subtracted. So the derivative of 4t cubed is really just the derivative of t cubed times 4. Derivative of t cubed is 3t squared, and that becomes 12t squared. Then we find the derivative of this negative 3t squared, which is really the derivative of t squared times negative 3. The derivative of t squared is 2t times negative 3 is negative 6t. And find the derivative of just t. The derivative of that linear function is just going to be 1. And the derivative of this last term, a constant, is going to be 0. And so we put it all together, we get 12t squared minus 6t plus 1. Running a little short on time here, so I'm going to just show this last example and let you look at it. We're rewriting things first, and then finding the derivative of each of those terms separately, and ending up with our final answer.